many people? Oh, there are already people watching. Oh, 2 minutes has passed. Oh, sorry. Okay.
Vin, it's
Welcome.
okay.
Yeah.
I still have to get Twitch set up, so there's no rush. But we just have a couple people that are gonna pop in to see what's up by the looks of it.
Yeah. But if you have not paid attention to past lecture, if you didn't know what is vector space, linear transformation, linear operators, that's fine. Because for today's slides, the only thing you need to know is about matrix multiplication. Yeah, that's the only thing you need to know. We won't be talking about linear independence, etc., etc. No.
Well, I mean that's good to know because I stopped studying a couple weeks ago.
And actually, I stopped studying in school for years. And then while waiting, and then I posted a link. That's a link linking to an HTML slides that I did a couple of years ago. That's about just to show you guys 数doku. And then you might wonder, wow, what's the relationship between Sudoku and determinants there? If that's my first question for you. And then, if anyone can answer, then wow, I would be so happy. And yeah, this one is to introduce proof by contradiction, but I don't think we will be using this today. Just to show you, oh, it's possible to, yeah. This is not a picture. These are HTML tables, and then yeah, just to show you another pattern. Okay.
All right. Well, welcome in everyone. I think who do we have? We have Darp. We got Shangostein. We're going to do eigenvectors and eigenvalues, I believe, next week.
Wow, my accent is so obvious. Yeah. Yes.
Hong Kong people unite. Yes. Hello, Martin. Welcome in. Thank you for the raid, Zach. We are just about to start up our 8th linear algebra reading group session. We are joined today. Is it okay if I call you? Is it Vincent? Is that okay?
Yeah.
So we're joined today with by Vincent. Vincent is going to share his love of mathematics in various ways and talk a little bit about determinants. So that's what we're up to today. And Vincent, you have the floor. I will monitor chat, and I will lend the floor to you.
Yeah, thank you. So, but I have to apologize to you guys first because the main focus today would be about permutations. Is to provide you another angle that schools won't usually teach you. So with the calculations shown on my slides, probably you won't be able to do much of the exercises in the book. So and why I'm doing this is because with another guy who wanted to present but turns out that won't present, we didn't like the approach in the book separating determinants of order 2 and higher order, and that's what you will see if you search on wiki. Of course, I won't be reading from wiki. And then from wiki, what you see about the definition here is, wait, where is it? It is this one. That's what you're gonna see. And then the book tells you nothing about this formula. That's why, and in this formula, it doesn't make such distinction between the number of rows, whether it's larger than 2 or 2 or below. So that's why I'm making this, so that you can comprehend much better. You are more comfortable with this. And then from the properties here, the introduction is heavily reliant on the linear structure, and then I'm trying to show you that there's another way to do it without much linear structure. So that's why I'm in my whole presentation, and then I will be undermining
the role of linear structure, and then I will just put it at the end of the slide, and then yeah, if you're interested, and then this will be really obvious from the definition itself. That is the definition of determinants, as you can see. And then okay, that's what you're gonna see on wiki, and then I make some colors to give it different, yeah, so that it's easier to focus. So here it is basically we have a matrix of a set called R. And then for this set of R, I only give it addition, subtraction, and then commutative multiplication. And then at the first time, I'm not requiring division at all. So question for you. Do you know why I don't assume that it is a field, and then I don't assume division at all, but only these three these three types of arithmetic operations?
So I personally don't know why you've just decided on these things. Maybe somebody in chat might know. We have a couple people typing in Discord. We'll give them a few seconds. Maybe because division is not defined for matrices. That's a good suggestion, George. Based on the way that Vin I don't know if that's what he's looking for.
Not defined. It's near. It's near. Oh, heifer. Oh, the name sounds French. That's close. Yeah. Division not defined for matrices. It can be. It can be. It can be. Animation system. Wow, that sounds advanced. Sorry, my stuff is really primitive. It's defined for empty matrix.
Are you able to put up that slide again, Vin, so that we can look at it?
This one, I love it. I love it.
They don't give a wedding ring to whoever gets his answer. Oh my gosh.
Yeah. So, your answers are near. So, say for example, if I want to define the determinant for a matrix like what? Let me see.
Oh, Dojo has an interesting suggestion from Twitch. Dojo says an algebra doesn't need to be a field.
I'm not that good at abstract algebra, to be honest. Even though I will be using things like Sn, but I won't talk about group structures at all, to be honest.
Okay.
Say for example, the answer is really simple. Say for example, I see stuff like this. I hope my latex is correct. Okay, my technique works. Say for example, and then we consider a set like 2025 because today this year is 2025. So here in this set we have no multiplicative unity, we have no multiplicative inverse. So, but if we see a matrix M defined on this set, defined over R and with elements in R, and then we can still say that, oh, the determinant of M is, oh, these two elements minus by the product of another diagonal at the anti-diagonals. That's why. That's why in the definition of determinants, you see only multiplication, and then of course the sign it will be either +1 or -1. But this +1 or -1, it will be assimilated it will absorb by an element, a factor in the product. So that's why we are not even requiring multiplicative unity in this set R. My abstract algebra sucks, so I forgot what the right kind of set will be. Is it? Anyways, let me find it out later. So here, since we will be talking about permutations, so permutation treated like bijection, defined bijection with the same domain and codomain. Yeah. And then Sn is a symmetric group of degree n, but we won't be talking about anything about group structure at all. And then to help you focus, I will use the red color for the input here. That's why you see. Let me. What? Here, I will try using the red color for the input for this I, and then the blue color for this sigma I. And then sigma is a permutation. So before I proceed, not this one. Let me give you a visual intuition about what this is. So let me see. Wait, I will jump to page 60 something. Where is it? Oh, it is here. Yeah. Okay. Well, sorry, I'm not that familiar with Adobe Reader. Let me think about this. Okay. Here you are. So here, this is a visual intuition of the definition of the determinant here. So this is just to give you a visual intuition. Actually, by a bijection or permutation, and you may regard each chosen cell here as a blue cell, and then the product you see, it is to multiply the blue cells together because of a bijection, and then that's why each row and each column has only one blue cell. And this is a visual intuition, how you can visually interpret this. And then we as for each permutation, and then we assign a function called SGN, called the sign of the permutation. And then we are adding up all possible such arrangements of blue cells. Yeah. So this is actually something much simpler than Sudoku. In Sudoku, you have, what do you have? Well, I'll close the slide. In Sudoku, you have 9 types of different digits. And then you have to ensure that for each digit is the unique, is the unique. There's only one occurrence of such digit in each row and each column. But here we only have blue cells, and that's all. And then okay, and this is the visual intuition. What are these? You can say so, but okay. So actually, each blue cell, it would be yeah. So example here, it would be we will first fix a permutation, and then we will mark each blue cell to be yeah. Just like a function graph, yeah, because yeah, sigma is a function from 1 to n. Yeah. this is just to give you a visual intuition. Okay, and then and then before I proceed, let me give you a not so complicated but not so easy example. That's the rule of Cyrus. So here, imagine that you have a coin, and then we mark 3 points, and then 1, 2, 3, and then if we swap the number 2 and number 3, and then the coin will be reversed, and then here its sign is not -1, and then if we swap 1 and 2, and then the sign is also -1. But if we swap it 2 times, sorry, I'm too tired to draw the picture for it, and then the sign would be 1, and then we repeat it, and finally we get the formula for determinant A. So from this, it is quite intuitive for us to think about to define the sign of a permutation from the number of swaps. So, and then, yeah. So here, say for example, and then this one, if you swap, yeah. And then a swap is just a specific example of an n cycle. A swap is actually a 2 cycle. Say for example, if you see 1, 2, 3 here, that means to map 1 to 2, and then from 2 to 3 to map 3 to 1. And, yeah. So actually, this is a clockwise rotation of 1/3 cycle. Yeah. Yeah. And actually, yeah, that's a nice answer. And actually, I only consider one type of digit. Yeah. And then the other two, and I will just forget about the digits from 2 to 9. I will just forget about them. Yeah. Okay, so let me get back from this slide. And then here. And then we found out that by some plastic calculations, we found out that, a clockwise rotation of 1/3 cycle, this is just, yeah, this is just, yeah, an anti-clockwise rotation of a 2/3 cycle. And then I picked this simple example just to say that the transform pathway is not unique here. So the problem with defining the sign of a permutation from number of swaps is that you need to show that the parity of the number of swaps is something stable, and it won't change if you have chosen different pathways. So what will we do is to try to show that for each swap, and then what we will do is that we will try to define something called inversion, and then we will try to count the number of inversion. And then what is inversion is that if, say for example, you have in a permutation, if you have found 2 inputs here, smaller input and then smaller than a larger input, but after the permutation, and then it changed. And it become the smaller input output has become larger than the larger inputs output. So for the sigma I graph that I've shown later on, and then it will goes downwards in the sigma I graph that I've shown later. Let me see. This one. So here, this is a sigma I graph, and then each inversion is actually corresponding to an occurrence of, how can I make it draw here? How can I make a pen here? Wait, no, this is for signing. Wait, sorry, I'll switch to Firefox because I know that Firefox has annotation tools. Sorry for waiting. Let me see. Wait. Not this one, sorry. Okay. Okay, so sorry for the waiting, and let me see, highlight color. Not highlighting, but okay, here. So actually each inversion is like this. If you see something this, and then you can see that, oh, one inversion occurs. So say for example, if I choose a sigma to be like this, and then just forget the yellow star for the moment, and then you just need to count how many such how many transitions from one cell to another cell, right and downward transitions that occurs. So here you see 1, 2. So here you see that this n of sigma is equals to 2. So the sign of this permutation is positive 1. Yeah. This is basically the graphical intuition of this one. So under this graphical intuition, and then the special point is that this way of defining the sign of a sigma, it is independent of the swap pathway. Yeah. For words that is not rigorously defined, I put them with double quotes. These are just to try to capture our verbal intuition. Yeah. So once we are able to prove a technical lemma that each swap can change the number of inversions by an odd number, and then we are done. Why is this so? Because yeah, once we have this little lemma, and then suppose that we have two different permutation pathways, and then for each pathway, the sign will be swapped once. So here it will be swapped, say for example, it will be swapped an odd number of ways, odd number of times. And then if you take the right pathway, and then it will be swapped if there's an even number of swaps, and then it will be swapped, the sign of a sigma will be swapped even number of times. And then so if you arrive at sigma here from the identity transform, and then you find that the sign one side on the left pathway, oh, you find that, oh, the sign is negative, and then on the right pathway the sign is positive, and then from the definition itself, which is path independent, and then you'll get into a contradiction. So that's why we need to that's why we can be reassured that the parity of the number of swaps is only depends on the permutation itself, but it doesn't depend on the swap pathway that you are choosing. And this is one of our first main goal in today's presentation. So these stuff are not so easy to be presented, to be explained on slides with my pictures, and then drawing each picture takes time. That's why schools usually won't teach you this kind of stuff, but I found it quite interesting, and personally I'm interested, I'm attracted by these kind of drawings. That's why I'm sharing with you today. So here I'm omitting the red row 1, 2, 3, 4, 5 until n, because that's always the same. Yeah. So I'm omitting them so as to save more space for much more annotations. That's the first reason. And then I'm using some poker patterns to denote them, because I don't want you to look at the alphabets or digits and then get distracted by all these stuff. So that's why I'm choosing these patterns. Okay, so how can I switch? Let me see. Page fit, yeah. So here, this is not a cycle. This is just an n-tuple. Yeah. So our goal for proving the technical lemma is to show that the number of swaps after swapping two chosen elements, like the heart with the tile, and then the number of inversions will be changed by an odd number of times. So here, so to count the change in the number of inversions, so what will we be doing is that we will use the general problem solving strategy called divide and conquer. And then first of all, I will try to show that so here I will try to show that every term that is outside the pairs of numbers to be swapped that are contributing to, that might be relevant to this n of sigma, it will be yeah, and then it will be this one, and then you will choose, for example, okay, I forgot the pen, sorry, let me see, where's the pen here? No, this is highlighter, sorry. Say, for example, if I am looking into these two, and then after the swap, and then it will become these two. So, say, for example, if this blue club is bigger than this blue heart, and then after the swap, this big blue cup, it will also be bigger than this blue heart. So you will still see. So after the swap between these two boxed elements, and then the inversion doesn't, it's still there. It doesn't vanish. So here you have it. And then and the same goes for, yeah, the same goes for, let me choose another color. Oh no, I'm not choosing the blue color. This color. If I choose this one, and then wait, I'm not highlighting the heart again. Wait. So for example, if I choose a spade, and then it's the spade is larger than the tile, and after the swap, and then you still get the same kind of relation. And then actually you can replace a larger than by a smaller than without changing the meaning at all. So this will include every cases. Okay. So I hope that you are convinced why. Wait. I hope that you are convinced why this there's so why terms outside the two boxed elements that are to be swapped won't contribute to this number, that is the number of inversions.
Yeah, that's a really nice visual. I like that a lot.
Yes. Thank you. And then after that, we will consider the terms inside these two numbers to be swapped. So here I'm including, so here there are three cases. Here this is the value that is below the two blue values. So let me explain this a bit. Actually here, the higher the sigma I value, and then the higher the vertical position will be on this graph. And then here I try to use this picture to capture the three cases. The first case is below. The first case here is, maybe I'll say case A. This is below these two, strictly below these two boxed values. And then the second case, case B, would be strictly in between these two values. And then the third case would be what? It was strictly above these two values. So this is before the swap. And then if there is an occurrence of an inversion, and then it will be marked by bolded straight lines, so that, and then after the swap, oh, the annotation says, oh, never mind. So after the swap, you will see that there is an even number of change for each element, for each actually this is a row index, for each row index. No, this is a valued mapped by sigma of a row index. Yeah. This is not a row index one. Yeah. No. You can see that there's an even number of changes in the number of inversions here. So maybe I will clarify.
Yeah, I think what you're saying is like when we go to make that swap, there's going to be a change that happens with both the diamond and the heart, right? So there's always an even number of changes that happen every time we do that swap. Yeah, yeah.
But a okay. So here I give you a little exercise. It is I left out the case 2. The case 2 is just that the heart is higher than the tile. So because I'm too lazy to draw another graph, and then that's why I left this as so-called exercise. So I hope that you're convinced. And actually, what I'm trying to illustrate with this proof is actually the proof number 5 of Wiki's parity of a permutation. And then in Wiki's proof of the parities of permutation, and then what's actually shown is actually a block of text like this. So I've chosen to show this first because this is the most straightforward proof that I can think of. So now we have the definition of sigma of a permutation, the sign of a permutation. Yeah, SGN of sigma. So let's try the first example. That is a triangular matrix. And then to test our understanding on the definition of determinants presented in this slide. So here, upper triangular matrix, that is a square matrix with 0 entries below the diagonal. Yeah. Yeah. The entries below the diagonals must be 0. Yeah, that's the definition for upper triangular matrix. And then for lower triangular matrix is that the entries above the diagonal must be 0. Okay, so here we have a little fact that the determinant of each triangular matrix is actually the product of its diagonal entries. So the normal way that schools will teach you to calculate this is to use the cofactor theorem that will be proved later, and then you expand, you choose a row or a column that has only one entry, and then you expand along that row or column, and then you reduce the size of the square matrix. That's the usual way to really do exercise questions, but here I'm just showing you how to use this definition to calculate stuff. Okay, so the observation is that if you randomly pick a permutation, and then that is if you randomly mark some cells to be blue in a way that that is depicted later, so that each row and each column has only one blue cell, and then probably very likely you will hit some zero cells. Yeah. So so here, but so without loss of generality, I'm simply assuming that this matrix is upper triangular, and then we recall the definition of a triangular matrix. That's something mechanical, and then we observe from this definition that we need to focus on permutation such that we need to focus on permutations that are not hitting cells below the diagonal. So this is a symbolic way to represent this. And then you might try to, say for example, assume that, oh, the identity transformation, you might try to assume that because the case when sigma is equals to identity transformation is trivial. So I'm trying to assume that, oh, this sigma is not identity transformation, and then we try to find some cells that is below the diagonal, that is zero. And then I'm not that good in this kind of symbolic logic, so this kind of local argument, so I hit the dead end, and then we observe that the given condition, say for example, sigma is a bijection. This is a global condition about the domain and the codomain, and then the sum that's over the whole Sn. I have the intuition that these are all global conditions. So what we will try to do is to consider two different sums. The one is the sum over sigma I, with I running from 1 to n, and then another one is just summing from 1 to n. So due to the fact that sigma is a bijection, so two sums should be equal. And then we have considered with this condition, we have imposed that sigma I is greater than or equal to I. So each term in this sum should be non-negative. So a sum of non-negative terms equals to 0. So the answer is easy. So each term is 0. So for each I, sigma I is equals to I. That's why sigma must be an identity transform. In this way, we have proved that actually this summation sign can be taken out. The sign of identity transform is 1, and then this sigma I is actually I. So finally we get T subscript I comma I. So similar arguments also applies to lower triangular matrix. So, yeah. Okay. Actually, the blue star is hmm. Let me think about it, how to say that. Actually, the blue star here is, let me go back. That's a good question. Wait. Let me grab a pen. That's a good question. Actually, the blue star here is some column index. Actually, it should be a particular column index. Okay. And then with value in between the two boxed symbols. Yeah. Okay, so here I'll give you another proof. That is proof number 2, I think. Yeah. Proof number 2 is based on Vandermonde polynomial. And then, to be honest, I had a hard time to understand this. It took me a whole afternoon to understand this. So on wiki, and then the explanation is really simple, and then it simply says that, oh, this is really obvious, but I'm breaking down every step here. So we are abusing the notations here. Actually, sigma should be a function taking one particular value to one particular row index to another row index. But oh, here, because we are using division, so we are assuming that we have a field value here. Yeah. So, but I'm abusing the notation and then use this on two tuple here. This is not a two cycle. This is a two tuple. So from the first bullet point to the second bullet point, the only thing that I did is to put everything under subscript, and then because this two tuple has already the order structure, so I'm not changing anything much. Okay, so the trick here is that here we have one here we have one way of establishing correspondence by one-to-one correspondence between the set of denominators here and numerators on top. And then actually we have another way of establishing the correspondence. Here we are choosing the minimum and maximum elements from the numerator. So each subscript under the numerator, it will represent a column index. That's why I mark them as blue. And then it's obvious that this such kind of S dash and then T dash, they are another bijection. Yeah. So if we compare X sigma S minus X sigma T, that is the that is a so-called polynomial. No, not yet polynomial. Sorry, not yet polynomial. And then with this xs dash minus xt dash, and then we will find that if here, because we are simply taking s dash, this is a minimum. So if sigma s, this one is smaller, and then this one is larger, and then if s dash is smaller and then t dash is larger, and actually they will be equal to 1. So in another case, otherwise it would be -1. That would represent the case when inversion occurs. Oh, I forgot to say that if you are puzzled at any point, and then please don't hesitate to open the mic and stop me and then ask me to explain.
I just wanted to clarify on this slide here, Vin, when you're talking about the subtraction in that numerator and denominator, you're just looking at the sign of the overall output, right?
Yeah.
Yeah. Okay. So it's +1 if it's positive and -1 if it comes out to be a negative fraction.
That's it.
Yeah. Okay.
And then actually on wiki you will see that there's a term called Vandermonde polynomial, and then this can simplify our writing. And then basically you just it's just a collection of factors with picking any two numbers in order of according to the order of appearance here, and then you just put the former number here and then minus by this later number here. So using such notation, we can actually rewrite and simplify sigma of the sine of sigma in this form. Yeah. So, and then there's a little exercise. Actually, this is called transposition, but I use swap so that you'll be reminded that such two cycle, it means swapping two numbers, swapping P with Q. So here there's a little hint, and then you can consider if you swap P and Q, and then you can consider this that these terms xi minus xp multiplied by xi minus xq in this Vandermonde polynomial, and then you see that after you swap them, and then here I is any index that is not equal to P and Q. Sorry, I didn't mark that. maybe it's better to quickly make some annotations and then mark that I is not equals to P and Q here. This is very important. So in this polynomial, you will see that after swapping P and Q, and then the relevant terms involving P and Q, they don't change. Of course, you can repeat, say for example, you can repeat for other cases like when this is the case when I is this is the case when I is smaller than P and Q. And then you can repeat with other cases. And then you will find that for 3 types of cases, the sign of those pairs don't change. So the only pair that has changed, that is, let me see, that is xp minus xq. And then if you swap it, and then if you swap p and q, and then the sign will be changed. So here's another lemma that is to test your understanding on the Vandermonde polynomial. But after writing this, I found that this is not needed for the development of the basic facts later. So I'll be skipping them and leave you as an exercise. Okay, so here I'll talk about the next example, that is from the Vandermonde matrix. So before talking about calculating the determinants of a Vandermonde matrix, so here's some applied math motivation here about the least degree best fit polynomial here. So, for example, here I have n given points on the coordinate system, and then I want to find a least degree, that is a degree n minus 1 polynomial passing through these n points. So finally, you will arrive at a system of linear equations whose coefficient matrix is the Vandermonde matrix. If you have heard of a Cramer's rule, and then you can solve linear equations with calculating determinants. That's why we might want to know the determinant of this specific kind of matrix. Here in the picture on the right, we need these n points to be distinct, but in the Vandermonde matrix, we don't need these T1 to Tn to be distinct. It is possible that, say for example, T1 equals T2 or T2 equals Tn. That's possible. So to calculate its determinant, again, we recall the definition. That's a classic move. And then I will try to, no, here is still recalling the definition, because each element in the Vandermonde matrix is defined by Ti to the power j minus 1. I represents the column index, and then j represents the I represents the row index, and j represents the column index. That's the usual way of representing things. And then this is just recalling the definition here. So of course, there's an easy proof, that is to use the factor theorem, use the fact that the determinant function is multilinear, etc., and then that will give a pretty easy proof. But I really want to show you how we can use this definition to show how we can apply this definition to get the classic result. That's why we will start from the Vandermonde polynomial. Okay, so from our previous discussion, we know that the sign of permutation, it can be expressed as the ratio of two Vandermonde polynomials, like this. And then actually I'm puzzled. And then instead of looking into books, I just sit down and then try some small cases and try to get some intuition from it. So I'll try a really small case with n equals to 5, and then with sigma equals to the swapping 2 and 4. So here I just do some yeah. So here I just make a simple observation here. So here we see that 1 maps to 1, 5 maps to 5. And then here when we see t1 to the power 10 and then t5 to the power 4, intuitively we know that we have to, in this product, we have to take as least t1 as possible and as much t5 as possible in the Vandermonde polynomial. So what we are trying to do is to try to look at the Vandermonde polynomial. Say for example, I fix any row index I. Say for example, I equals 2, and then I observe in the Vandermonde polynomial the terms containing the row index that is being picked. So here, say for example, since we have said that we try to avoid T1, so we are picking here, and then we try to pick as much T5 as possible. That's why we are taking minus T5. Considering product of differences. Column swap. Yeah, that's a classic way to solve problems. Yeah, that's what I did when I was an undergrad. Okay, so and then since here we see that the degree of T2 is 3. So intuitively, we know that we have no choice. We have to pick T2 in the two remaining factors in the Vandermonde polynomial containing T2 here. And then to help me thinking, I'm just putting below each red index the corresponding blue index here. And then I make a little observation that 4 here, say for example, 4 here, it is greater than 1, and then 4 here greater than 3, etc., etc. And then we see that why we are picking 2 instead of 4, why we are picking the red 2 instead of red 3, and why we are picking the red 5 instead of red 2 is determined by the blue value actually. To understand this, imagine that there are two red players playing a card game. And then these two players with red colored index, red number, they each play a blue card with a blue number. And then the player having a greater blue card value, it will win. And then it will take the token. And then finally, for each player, we count the total number of tokens or total number of coins. One from other players. And that would be the degree here. So we are trying to make some generalization or abstraction from this little observation here. So we replace here, what are we replacing here? So here we are fixing one, we have a sigma fixed here. Because sigma goes first in the definition of determinant. So we fix sigma first, and then we consider this product here. And then, let me see, we are replacing this because we want to explain the, wait. Here, yeah. We want to explain the degree, and then that's why we are replacing 2 with I here. And then 2 maps to 4, and then we replace it with sigma I. And then here 1 and 3 here, we here 2 is compared to 1 and 3. That's why, and these are terms that is being picked. We are not paying attention to 5 because in this term here, we are picking T5 instead of T2. So here we are choosing 1 and 3. These are to represent terms present in Ti. But and then with a row index with the red value that is either smaller than or bigger than our chosen red index here. So here we observe that the term with a larger sigma I, with a larger blue value, that is a value mapped by the row index mapped by, anyways, the sigma of a row index, that is a column index. We are choosing a larger one. So we want sigma I to be chosen. That's why we want to reassure that sigma I is strictly greater than sigma I dash. And here we want sigma I to be strictly greater than sigma I dash dash. And then here and then this is just a word game to see that this one is greater, this sigma I is greater, and then this sigma I dash is smaller. That's why, wait, where is the, maybe I'll choose a blue pen here. It goes like this. This is sigma. Sorry, I don't know why it doesn't work at the moment, so I'll just forget it. And then here we have a sigma I, and then sigma I is higher, and then a sigma I dash dash is lower, so it goes down. And then if it goes down, there is an inversion here. So since there are sigma I minus 1 blue values that are smaller than sigma I, that is from 1, 2, 3, blah, blah, blah. up to sigma I minus 1. Those sigma I minus 1 values are strictly smaller than sigma I. That's why the degree of Ti is sigma I minus 1. And then here we have to count the number of inversions here. And then that is so here we are trying to count the number of inversions inside a inside a yeah. Let me think about this. We are counting the number of inversions inside what? Okay, sorry. We are trying to count the number of inversions in the Van der Waals polynomial of this Ti from Ti to Tn. So here we observe that we are only counting the wait. Actually, we are counting the number of minus sign in Ti. Sorry, yeah, in the Van der Waals polynomial. Sorry. So here we have so we observe that when there is no inversion, and then there will be a minus sign. And if there's an inversion here, and then you will see no minus sign. So finally, you have for each fixed I here, you are counting the number of non-inversions in sigma. So finally, we add I up from 1 to n, and then we found that, oh, this is actually the total number of non-inversions in sigma. So the total number of inversions is here, and then this n minus 2, actually this n minus 2 comes from the definition of inversion. It comes from here. A two tuple here with s strictly smaller than t here. So So finally, to wrap up, and then we make some plastic calculations. And then we found that this thing looks really like Van der Waals polynomial, but with a constant factor here, -1 to the power of n choose 2. And then since this is -1, and then we don't really care whether the here is plus or minus or not. So finally, here we just factored out the -1 to the power n minus 2, and then yeah. So we invert this sign here to reflect that, yeah, so that this factor is absorbed. Yeah. So after going through all these, this is just to show you, actually the purpose of doing all these is just to show you that this is a classic result. Yeah. The determinant of a Van der Waals matrix is equals to the Van der Waals polynomial of, let me see, can I write here? I can't. That's bizarre. Never mind, just forget it. This is just to show that it's the permanent, it's the Van der Waals polynomial from Tn minus 1 up to T1. This is a classic result, and then this is just to show you that it's really difficult to use the definition of the determinant to make actual calculations. That's why we are trying to prove 3 basic facts. The first one is the determinant of a matrix, it is equals to the determinant of its determinant of its transpose. And I don't know why I put this lemma here, and then this lemma is just to show you some skills, this how to operate with this definition. And then here we have a row here, and then this lemma tells you that we can insert a row to the left of I here, and then the reason is that the reason is that actually this product sign, it is collecting every key value pairs here, so it's invariant under permutation row. But it turns out that it's not that relevant to the proposition itself. But anyways, it provides you some tools to operate with this definition. And then the proof here is basic. The step is to again recall the definition, and then I have a convention. That is my convention to, if there's a matrix and then I don't want to use another symbol, and then I'll just put a bracket, and then with this capital letter representing the matrix, and then with 2 small subscripts representing the row and the column index of the so here the key technique here is to see that I can't use the pen tool. That's bizarre. Never mind. Yeah. Let me see. Page fit. Good, 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 good. Okay. Oh, that's bizarre. Anyways. Okay, here if you see something like sigma I to I, you can imagine that row index is like, oh no, I should have chosen the red color for row index. Yeah, give me a second. From sigma I, and then we have oh wait. Here we have from sigma I to blue index I. Here, wait. This one, let me make it black here. And then we have blue I here. And actually, let me think about this. And here we can also make, choose another color, I here. So actually this sigma I, it is actually another function. There's a function in between I and sigma I. So I'm trying to draw another arrow representing such transition. Here actually, okay. So here I undergoes sigma to go to sigma I. So here it is the identity transformation. So that so you see that from each row index, it is actually from each row index, you actually goes reverse this sigma before undergoing the identity transformation to get to, wait, why am I marking this as red? This should be blue. Anyways, I hope you get the idea. So here you have sigma I, we reverse this sigma, and then so as to get to the column index. That's why here I'm writing I, and then here I'm writing sigma minus sigma inverse of I here. And this is a skill that you can apply when you are doing this kind of derivations. Okay, so another trick is to replace sigma SGN of sigma by SGN of inverse of sigma, so that it will match, yeah, what's inside the bracket following SGN will match here after the red index. Because in the definition of determinant, you see that the element of Sn, it matches what's preceding the rightmost blue subscript. And then here we can safely replace SGN sigma by SGN sigma inverse. It's due to the fact that it is due to the little fact that we have proved Actually, it's not due to the fact that we have proved earlier. It's you don't need to prove this so-called lemma. This is just a practice of Van der Waals polynomial. And then actually it comes from the fact that comes from our intuition about the sign function as the parity of number of swaps. So here, let me show you the graph. So if we have sigma of, if we have SGN sigma as number of slopes going this way, and then actually SGN sigma minus 1 is just the number of slopes going reverse way. So the number of slopes should be equal, right? That's why I can safely replace sigma SGN of sigma by SGN of sigma inverse. Okay, let me see, where am I? So ending the proof of basic fact number 1, and then there's another basic fact number 2, and then actually if you swap 2 rows of the determinant, the sign will be alternated, and the proof of this fact is actually independent of the proof of the first fact, and independent from what you have seen in the book. Okay, so here that's another little lemma. Okay, so here we have a tau that is fixed, and then if we either apply it up in front of this sigma, which is the index on which we take the summation, either before or after, and then it won't change the determinant itself. And then the proof is quite simple. It's because again, either tau sigma or sigma tau, they are running through the entire Sn. So this tau is just like some sort of translation. That's why we are still summing over all permutations. So this is pretty intuitive. And then to try to represent swapping rows, I try to use an elementary matrix, with 2 rows swapped. And then I try to argue that determinant of MA is equal to negative determinant A. So the proof, the skills is again classic. Just directly apply the definition, and then I do some IJ stuff, IJ plastic calculations, and then and then again, this is the skill that applied. Again, the same skill. If you don't want to look at the lemma, and then you can simply draw a diagram just like what I did here. What the just draw the diagram here, and then you'll find the relation between row index and column index.
Yeah, so Anders was asking a question in Twitch chat. I just posted it there for you to read, Vin.
In the definition of determinant A transpose, in each term appears in determinant A. They just appear in.
So he's wondering if that's the intuition that that you're thinking about in your proof.
Definition. So the values are the same. Yeah. It turns out that they just appear. Yeah. Each term appear, let's say determinant A, they just yeah. And how do we know that? It's by this kind of deductions. Yeah. Drawing this kind of graphs. Sorry, it's not that well. Wait, I should. This. Is by drawing this kind of math, this kind of picture deduction, and then
Anders says thank you.
You're welcome. So finally, I added a tau here so as to balance the equation. And again, here we find out that this is the pattern we see in this so-called lemma, and then we are simply concluding that oh, this is negative of a determinant A, and this end is little derivation. Okay, so and then if we apply the first fact, and then we will know that oh, this is a, and we can see that this also applies to swapping columns. Of course, you can, as an exercise, you can try to derive it yourself to test your understanding if you want to torture yourself. And the third fact would be a bit more tricky to show in permutations, but this is still doable. So here I immediately apply the here I apply the definition here. So the ijth entry of a matrix product, and then this is something really mechanical. And finally, I arrived at, and then I was stuck at this point for a while. That's why I write all these stuff to remind myself in case that you are not comfortable with it. Basically, if you invert a product of sums and then with equal number of terms, and then and then if you invert it, and you'll find out that this sum here, it will be a vector. Yeah. And then this vector is actually some kind of choice function. Yeah. So I'm simply applying this basic fact, and then I write in this form. And after that, it's normal to get stuck because in the product in the right, we see that there's two permutations. But here we only see one permutation. So how can we get another permutation from this choice function? And the way is to see that if this vectors v is not bijective, and then the contribution to this sum is 0. So how are we doing that? Again, I do that by intuition. by some particular observation first. So here I put some symbols so that you'll be focused on the numbers here, and then the numbers here, these are just a symbol here. Yeah. So here, what I attempt to do at the first place is to apply a swap on the column index here, on the column index sigma I here. So in case that vi dash I assume that for some row index I dash and I dash dash, and then I assume that vi dash equals to vi dash dash, because we're given here v is not injective. So we put this assumption and then we apply some swap, and we observe that after the swap, and then we are still taking product over the same set of terms here. Yeah, these terms to be taken product is are still the same. So here what we will get is that we will arrive at something like this. And since we have applied tau here, and then we attempt to put a tau inside this bracket so that these two guys match, but this is actually wrong. Why this is wrong? Because this tau here, it is dependent on this v. The choice of this tau is dependent on the v itself. So we can't do something like this. This is really wrong. So what we attempt to fix this is to dump this SGN bracket tau sigma inside this summation. Before we apply tau here. Wait. What am I doing here? Yeah. So we first apply tau here, and then we apply tau here. And then we put a minus sign so as to balance the equality. But the problem here is that we don't have the previous lemma. What's the previous lemma? Actually, what we want is to apply this lemma, with tau here. This tau, it is in this lemma here, it's clear that tau sigma also runs through all the entire Sn. But the problem is that here this tau is fixed before this sigma. This tau is constant throughout the whole summation product process. But here, that's why what I'm showing is really wrong. And why am I spending time on this wrong stuff is to show you why we are applying a swap on the row index instead of the column index. So to solve this dependence problem, we apply to the row index. And then we'll find that, because these two inputs, I dash and I dash dash, they give the same function value under V. So either I applied row or not to either I swapped or not the input, that will have no influence on the function value. So that's why I have V row I equals to Vi for all I. So by doing so, I sneak in a row here. a permutation row here. And this row is invariant under the product. So finally, to balance, to make it look like determinants, so I insert a row here and then a negative sign here. And then up to this one, apply the lemma. And then this row, it is independent of sigma. I choose it. This row here, it is independent of a epsilon. And then I choose it according to V. Yeah. So it will be good. And then since this epsilon row, it runs through all Sn, and then I can simply replace it by a simple epsilon. And then I swap these two summations because the set on which these symbols are taking sum over, and then they are independent of each other, and then those are finite sums. So I can swap them with no problem. And after swapping them, we will get that left-hand side here is equals to negative of left-hand side. That's why this left-hand side must be 0. So finally, we can be reassured that we only need to consider V, which are bijective. And we rename V as row, and then, yeah. And finally, we will arrange a bit the terms. We are just moving this guy to the left of SGN sigma, and then summation order swap. Yeah, we are just swapping summation order. That's fine. And then here we are doing the same kind of operations here. And then we split this sigma into two different permutations. And finally, we apply the fact that, oh, this guy also runs through all Sn. So we simplify this into one single Greek alphabet representing the permutation here. And then we observe that these two guys can be factorized. And concluding the proof of this basic fact number 3. Okay, so with these 3 basic facts, we will be able to recover the book's definition that is based on Laplace expansion or cofactor expansion. So we have a little observation. I hope that you are familiar with it. I'll just quickly jump through this, and then what we are trying to do is to pick any row and then pick for each row, chosen row, and then for each element we circle it, and then we delete every row and we delete the row and the column containing the chosen element. So here we go back to the visual intuition here. And then the blue cells represents the terms after the product sign in the definition of determinants. And here I just wrote I represents a column index and sigma I represents I represents a row index and sigma I represents the column index of a particular permutation, and then we make a anti-clockwise rotation like this, so that it becomes a usual XY graph, something like XY graph that we usually see. And then here the star represents a chosen row, and then I make it I0 here. So we will now to understand the book's definition, and then I forgot to talk about one symbol that I'll be using is that A tilde ij. That means the matrix with the ith row and jth column removed. So because in the definition it involves a number of inversions. That's why we will be looking about the fact of removing one row and one column to the number of inversions in this permutation. And I call it star deletion to save ink and time. Okay, so I'll use a graphical argument because I found that I tried once to write symbols, and that's doable, but it's tedious and it's really hard to focus. That's why I've chosen to draw graphs, and I promise you each graph here it takes me 6 hours to draw. About 6 hours to draw. And that will be my last Beamer slice. Okay, so after the star deletion, and then I will mark the deleted row and column with this hatched area. And we observe that the number of inversions, that is the cells that goes right and downwards like this, it don't the number of inversions, that is the cells that go this way, that doesn't change. If it doesn't touch the star here, it doesn't change after this star deletion. And then this is really graphically intuitive, and if you want a really detailed explanation, I would say that to draw a fixed line like this, and then after the star deletion, and then the cells don't cross this border. That's why, these inversions and non-inversions without star, they won't be changed after this star deletion. And then we only need to focus on inversions that are involving star, the yellow star. So to count the number, and then count the number of changes of n sigma and n sigma tilde. The sigma tilde means the permutation after the star deletion. So to be able to draw some conclusion, and then I let this area, this region to be K. And then here we let that, we suppose that there are K inversions here. And then, so that means there are K cells on the left of K blue cells on the left and above this star. So here we do some counting, basic counting arithmetic, and then we count every numbers here, and then we found that yeah, after the star deletion, we will lose these number of inversions. And then it turns out that this number is it is I0 plus sigma I0. Mod 2, okay. So I do some really basic arithmetic, and then to derive at this formula that is about the, yeah. So after star deletion, and then the sign change would be like this. So to recover the book's definition, okay, so we will be, so we will be deleting I0 and sigma I0. So we, first of all, we extract this term out from the product, and then we apply this star formula here that we found earlier. And then we apply the star deletion. Yeah. So here we only relabel the terms on the right of the summation, on the right of the product sign, and then replace sigma I by sigma tilde I. Yeah. And then what will we be doing is that and then we want to move this, for example, in the book you see that this -1 to the power something, and then with the element chosen to be deleted with the star element that is on the left of determinant, that is on the left of the summation over the permutation. That's why, but here you see that, oh, here we have sigma here. That's why we will be applying a simple technique, simple lemma. And then here, this is just a simple warm-up exercise. Yeah. And then to decompose yeah, a sum of a function value as a sum of function, as a sum of value in the range with the count here. And this is basically, this is a number of counts of how many input will give this is a sum of frequency of y. Yeah. So this is pretty intuitive, and we will, according to this, and then I will give another lemma. And the reason why I'm giving this lemma is that this is to show you a more general fact, and to show you that this has nothing to do with the group structure of Sn. This is a simple counting argument here. And then I think I will be skipping this, and then you can look at the detailed derivation at home, and then I'm not that interested into this. And the point is that I use this little lemma to tailor-made for this guy and then for this sum and product, so as to extract this thing out of the summation symbol. And this is known as the Kronecker delta. If J0 is not equals to sigma I0, and then this guy will simply turn 0. So I just change this condition, write it underneath the summation sign so that I can get rid of this Kronecker symbol that is not present in our goal here. And after that, what will I be doing? Yeah. And then we will be, to finish this, we will be attempt to change this to Sn minus 1. So we will do some really simple mapping to conclude this. So, and then here we have J0, but actually this is not needed. Yeah, we can drop this I0, J, drop the 0 in I0 and J0. And then here, this means that we can expand along a row. And then for each row, and then we take an element, and then we delete, we take the determinant of the matrix with the chosen element, the row and the column containing the chosen element deleted. Yeah. So due to fact number 1, that is a matrix is equals to its inverse, the determinant of a matrix is equals to the determinant of the transpose of the matrix, and then actually we can also see that yeah, expansion along a column that also works. So this leads us to the final, yeah. So if we take a closer look into this sum, and then we try to relate it with matrix multiplication, and actually you can see that you can arrange them in this way with a column, with a matrix like C transpose. Yeah. So this slide is just to provide you some basic vocabulary, and then the determinant of ij tilde is called minor, and then this term negative 1 to the power I plus j, and then times the minor ij is called the cofactor of A, ij cofactor of A, and then sometimes it's denoted as Cij. And then we use it to form a matrix, and then we found that if you take closer look into the linear structure, and then you will see that A the diagonal entries of A C transpose, it is equals to determinant A due to the cofactor theorem that we have just proved. Cofactor expansion that we have just proved. Yeah. And then what's next is to observe the off-diagonal entries of the matrix product AC transpose. So here we are not going to do any expansion. So why this is 0? The argument is really simple. Here this is 0 because actually we observe that this I dash 1, it looks really like AI1. This I dash row, the entries look symbolically, it looks really like it. This I row. And then, so what we are going to do in this sum is to observe that this is actually this determinant, the determinant of the original matrix A with the ith row replaced by the I dash row of A. And then since we have two same rows here, and then by the corollary of basic fact number 2, that is swapping two rows alternates the sign of a determinant, and then now after alternating and then two rows with the same two rows with same entries, two identical rows, and then actually the determinant should be 0, right? This explains why off diagonal entry of AC transpose should be 0. So the conclusion is that AC transpose equals to determinant A. This is a number in R. Is equals to I. Sorry, ACT transpose is equals to determinant of A times the identity matrix. And here the identity matrix with 1, but when we multiply it with determinant A, since determinant A is a member of R, and then the 1 here will be absorbed by determinant A, so that this matrix is still a matrix on a square matrix on elements of R. So it is only at this point that we need division. If we want to calculate matrix inverse and then say that, oh, A inverse is equals to what? A inverse is equals to 1 over determinant A times C transpose. Yeah, it's only at this point that we need division in R. Otherwise, we don't really need that. So to test your, thank you for listening, and then there are some food for thought or exercise. Yeah. And then I've intentionally left out multilinearity. This is really useful, and then you can use it for proving Cramer's rule. Yeah. And then for alternative proof of basic fact number 3, that is, yeah, alternative proof is on wiki. Yeah, showing that determinant operator is unique, and then you can find that this is a classic result, and then I'm sure that you can find it on Math Stack Exchange. And then well, never mind. I think it should be an alternative proof for the cofactor expansion, but never mind, never mind. Because
No,
in a
it's
cofactor,
it's all good, man. All good. I just want to take some time to say thank you. I know we had a couple thank yous from chat from people that had to leave a little bit earlier. Like Adino had said thank you. Meow had said thank you, and for some of the interesting explanations that you provided today.
yeah.
So for those that are in attendance, we'll post the video up to YouTube, and we'll provide some links for you. And then if Vin is able to and wants to share his slides, we can provide those to you as well to
Actually,
look
the
at
slides is
afterwards.
already there. It's in a side chat. It's in a simple group discussion. Yeah.
Okay, perfect. Yeah, we'll make sure to link it to so people
If
know where
you
to
want
find
a
it.
source code,
Yeah.
yeah. If you want a source code, I can also provide it, but it will be about how many lines? Not gonna lie.
Your source code, I'm sure, is really huge.
This is not updated. I will find it. Source code is about. No, this is too few. It's about 1,000 something like. Yeah.
Okay, cool. Yeah, like so people want to play around with some of the drawings were beautiful. So if people want to play around and
Yeah.
kind of see how you did some of the work. Were you doing that in TIC-Z?
Text doesn't support it. I've asked on the official. Someone text me. Oh, it's the announcer. Okay. Actually, I asked on the group, and then let me find. And then the technical explanation from Texas official server is that for some packages, say for example, annotate equations. Actually, I've used annotate equations to give
Okay.
annotations.
I'm just setting up a raid
And then,
on Twitch, so thanks to all the Twitch folks that came in. Thanks again to Zach for the raid. We're going to bounce over and say hello to Phobos, and then we're going to be back tomorrow morning for our real analysis group. We have a lovely presenter coming in to chat a little bit about sequential limits and axiom of choice. So take care. To those of you on Twitch, we'll talk to you later.
thanks for listening. Okay, so